question 9. So this is about a golf ball being hit up in the air and returning back to the ground. So I'm going to draw a diagram for the path of the particle. So this is the path of the particle in terms of its x direction and y direction. So it's hit from the point O on horizontal ground here. The horizontal and vertical components of the initial velocity are 3u, so that's the horizontal, and u is the vertical, and that gives a resultant velocity in this direction. The ball hits the ground at the point A, where OA is 120 meters, so it's moving freely under gravity, so that means that this is a symmetrical parabola. And 120 meters later, it hits the ground. The ball is modelled as a particle moving freely under gravity. Show that u equals 14. So it would be handy to have some CVAP conditions listed out here. In the x direction, I know it's travelled 120 meters. Its initial velocity was 3u, and its final velocity, as there's no acceleration under gravity in the horizontal direction, will remain as 3u, so it's constant velocity. There's no acceleration, as I just said. In the y direction, it's left the ground, it's moved up, and it's returned to the ground, so its final displacement is 0. Its initial velocity was u, and in fact, because this is symmetrical, whatever its positive velocity is at any point on this side, the negative will be the same magnitude here. So this will actually be minus u if we want to use that. The acceleration is only acceleration due to gravity, which is opposite to the initial direction of motion. So I'm putting that as minus 9.8. I'm deciding that that's the positive direction. So show that u is equal to 14. Now, if I try to use, because there's no t here, if I try to use v squared equals u squared plus 2as, I end up with 3u equals 3u for this, which is useless. And I end up ruling out u for this one, so that's also useless. So I'm going to use s equals ut plus half at squared. It's not the only way to do this. But I'm using that. So in the x direction, 120 s equals u, which is 3u in this case, and t I don't know. I'm going to rearrange this for t. So 120 over 3u, and you'll see why I'm going to do that in a minute. So y is equal to, so s, which is 0, is equal to u, which is u, t plus a half a, so a half a is minus 4.9, so minus 4.9 t squared. Now I know that its displacement from the ground is 0 at time 0 and at some unknown time over here. So I'm just going to factorise out the t there. Because I know that t is either equal to 0 here, but I actually want this value here. So u minus 4.9t is equal to 0. So now if I rearrange this, u is equal to 4.9t. I'm going to substitute my value of t in from here. So that's actually 40 over u. I could have simplified that, so I'm going to put 40 over u here. And now multiplying both sides by u, and then square rooting, I get u equals 14 meters per second, as required. For part B, find the speed of the ball immediately before it hits the ground at A, so that's here. So I know that to find the speed of the ball, I actually need the to the vectors in the two different directions, y and x. So if I just make a little triangle for that, so to find the speed here, I need the magnitude of this vector. So magnitude of v, and I find that by using Pythagoras, using the vertical and horizontal components. So the vertical component of this is minus u, and the horizontal component is 3u. So I just need to calculate, and we know that u is 14, so minus 14 squared plus 3u, 3 times 14 squared. And that gives me 44.3 meters per second. For part C, find the value of t when the ball is moving at an angle alpha to the horizontal, where tan alpha is equal to quarter. So you can see that the angle between the particle and the horizontal is changing, or the velocity of the particle is changing as it goes through its journey. So I'm going to just make a little vector, a triangle for that. So at some point, if it's travelling in that direction, its velocity will make this angle of alpha. So its horizontal and vertical components, Vy and Vx, will be equal to tan alpha. So tan alpha will be 1 over 4. So this will be equal to 1, and this will be equal to 4. So Vy over Vx will equal 1 over 4. Now I know that Vx is 3u because that hasn't changed all the way through the journey. There's no change to the horizontal velocity. So 3u is 3 times 14, which is 42. I can just rearrange this equation now. Vy is equal to 42 over 42 divided by 4, so that's 10.5. I want to find the time when that happens, so let's just set up the new Suvat equations. It's not really useful to use the x direction because the velocity doesn't really change there. So in the y direction, SUVAT, u is 14. The velocity at this point when it's travelling in this direction is 10.5. Acceleration is minus 9.8. Doesn't matter that I don't know distance because I can now still work out time using v equals u plus at. So v, 10.5, equals u, which is 14, plus a, which is minus 9.8 t. And that means that at time 0.357 seconds, it's travelling at that angle. Now, if it's travelling at that angle on the way up, when it goes through its journey and comes back down the other way, it will also be travelling at an angle alpha to the horizontal here. So its velocity in this direction hasn't changed, but as you can see, we were just using the vertical direction. The velocity here, as I said before, will be the negative of whatever it was on the way up. So it was 10.5 on the way up, so it will be minus 10.5 on the way down. So we just need to change this to minus 10.5. Minus 10.5 equals 14 minus 9.8 t. And that gives us time 2.5 seconds. Marks wise for this question, and back up to here, there's a method mark for it in the y direction, making an equation where it's clear that you've used this or another Suvat equation correctly, If you've made some mistakes with sign errors and values, that's fine. You get an accuracy mark for all terms correct. But either way, all terms must be included. You also have an accuracy method mark for using some kind of Suvat equation in the x direction, and an accuracy mark here for rearranging either this or this, ready to substitute in, but you only get this if you've also done your equation in the y direction. Then you'll have an accuracy mark for a equals 14. For part B, there's a method mark for using Pythagoras to find the magnitude of that vector, and an accuracy mark for finding 44.3. You can leave that in exact form as well, 14 root 10. For part C, there's a method mark for making an equation linking the velocity in the x and y direction with the quarter. It doesn't have to be set out like this, but it does have to clearly link the two. And an accuracy mark for it being correct. So a equals 1, or you may have done the working out to show that it's going to equal to 10.5. Then there's a method mark for using a Suvat equation. Doesn't have to be v equals u plus at again, but it does have to be a correct equation, not with necessarily all the signs correct and everything. You get an accuracy mark if everything is correct. Obviously, if there's one error, then you don't get that accuracy mark. You get an accuracy mark for 0.357 or 0.36 in fact, and then another accuracy mark for finding the second value there.